Good day, grade 12 learners and teachers. Welcome to today's mathematics lesson. My name is Sibusiso Shongwe, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Remember, good people, we are also available on WhatsApp 064-748-8913. That's where you'll find us. That's where you can be able to ask questions that are based on the lesson that would be unfolding today. Right, if you recall, this lesson is part B of the lesson that we had last week. We are busy with interpretation of sketched algebraic functions. We've analyzed some papers dating back from 2015-2016, and when we looked at the marks in functions, graphs, and inverses, we picked up that more than 80% of the marks in an exam come from the content that you did in grade 11. Inverses contribute only a small portion. So it is thorough and proper that we do our revision of grade 11 concepts, and we make sure that we cover all bases that will enable you to get a lot of marks on these functions. Inverse functions are also very important. It's important that you also learn them and you know them as part of the grade 12 content. However, we are saying grade 11 content that you did last year contributes a lot. That is why also we invest a lot of time in terms of our revision of grade 11 concepts. Right, let's check the outcomes for today. By the end of this lesson, you should be able to solve inequality problems using graphical approach. You would recall last week I started with this section, and then from there I could not finish, and I promised you that this week's lesson would actually start on those inequalities to show continuity between last week's lessons and today's lesson. Right, solve nature of roots problems using a graphical approach. This can also be a problem in a sense that most of you would want to use the discriminant delta when every time someone gives you a question about roots, nature of roots, you think that you have to use the discriminant. But today you'll get to see that you can solve those questions using transformations, not necessarily the discriminant, because the discriminant has a lot of limitations. It works only for quadratic functions, but also in them it works only for limited questions. Right, you should be able to interpret sketched functions using all the skills that you learned on functions. Remember, those skills will include transformations, it will include vertical distances, horizontal and diagonal distances that we did last week. It will include increasing and decreasing functions, domain and range, intercepts, axis of symmetry, symmetry, asymptotes, all those concepts together in one. You need all those concepts, inequalities and graphs. You need all those concepts to be able to actually interpret functions that are sketched. So those skills are important, right? Obviously, we are guided by the CAPS document in this case. If you look at page 32, that is where there is a content clarification about what should be done on functions. Also on the exam guideline on page 6, they do provide a guideline there of what should be covered as far as algebraic functions are concerned. Right, obviously you don't come to this lesson empty-handed. You come with knowledge that you've gained in previous grades. So knowledge that would be prerequisite to this particular lesson would be sketching of all those functions: a linear function, a quadratic function, an exponential function, and a hyperbolic function. Right, and you are given those standard forms there. They are very, very important that you also note those standard forms in which those functions are written. Obviously, with a quadratic function, we can also add the ax squared plus bx plus c. It's also a standard form there that is very, very important. Now, effect of parameters also, you should know how these parameters are going to affect these functions. Domain and range as well, very important. Vertical length, horizontal length, diagonal length, as well as any type of length between the two functions, and transformations, understanding transformations in the context of algebraic functions. Yes, your teachers might show you what happens with transformation of points and all of that, but it is also important that you are able to apply the concept of transformation in the context of algebraic functions. Right. We go back to inequalities. Let us now first look at the notation as we did last week. The notation here, if you are using this type of a bracket here, it's not included, that is a round bracket, or you can actually use, if you are drawing a number line there, you can use an open circle there to represent now interval that is not included. And then if you want to include, obviously you use that square bracket, and then obviously you'll have your shaded circle or an oval there to show that the values are included. Now, if you check the third one, it shows that the first value is excluded, however the last value is included. Right, now let's move on. Now, these inequality problems can be broken into three different types. The first type, as we indicated in our previous lesson, is just those solitary functions. If you are given just a single function, maybe say a straight line is drawn like that, or you have that a parabola is drawn maybe like this, and someone asks of you, where is the graph? Let's say that these represent f. Someone says, where is the graph of f greater than 0? That person is saying to you, where are the y values greater than 0? Where are the y values positive? Where are the y values positive? So you are going to check now on the function where the y values start being positive, and y values are positive above the x-axis. You see, if you draw your Cartesian plane here, if this is the x-axis there, any y value above this line, which is the x-axis, above the line y equals 0, because the x-axis is a line y equals 0. So above this line, you get to find positive y values. So we're going to locate the function where it is above the x-axis or above the horizontal. So we're going to shade that region for this one. You can see that is the portion of the graph that is above the x-axis. Then you need to indicate the values of x for which that particular function would be above the x-axis. Right, now let's check on this one. If on this one they say also they want where f of x is greater than 0, so they are saying where is the parabola above the x-axis. So you're going to locate a portion of the parabola that is above the x-axis. So now if you look at this part here that I'm highlighting, it is above the horizontal. This is the horizontal. Also, this part here is above the horizontal. Now that you've located those points, you get now to then shade the region where that a particular function is above the x-axis, and then from there you are going to be able to locate the value of x, to say the value of x will start from here and it will end there. Also this side, the value of x will start from the left start from the left and it will end here, because when you analyze functions, you are always going to analyze them from your left to your right. That's what should happen. Should always analyze functions from left to right on the horizontal axis and from bottom to top on the vertical axis. Left to right on the horizontal axis, bottom to top on the vertical axis. That's very, very important. That's a method of analyzing functions, right? Also here, when they say f of x is less than 0, they are saying to you, where is the graph of f below the x-axis or below the horizontal? So you're going to check the portion of that graph that lies below the horizontal. And then here they are saying f of x equals 0. F of x equals 0. They are trying to ask you here, where is the graph of f at the horizontal? So at the horizontal, it's at this line, and at this line, it is what? The x-intercept. So line y is equals to 0 represent what? The x-intercept. It represents the x-intercept. So those concepts there are very, very important for you to be able to analyze these inequality problems. And you know, you've seen them in papers. They are always asked. So you need that particular skill, right? Now let's go to the second part here. Now we are no longer, if you check here, we're looking at a solitary function. It was just that one function. It was just f. What was happening to f there? So it was just the graph of f. But now when you look at this, there is now g that is infused there. But now what we are doing is we are comparing f and g. We are comparing them. And in order to compare two quantities or two functions, you need to know where they were equal first. For you to know which one is ahead or which one is above the other, you need to know first where they were equal. What is the starting point? So the starting point for any race, if these functions were looked at as functions that are involved in a race, and we are saying this one is going to win the race, it's obvious that you need to know where they started, and they start all of them at the same place. And in this case, we are going to then use their points of intersection as the starting point. In the context of functions, we are going to say we are going to use it as a critical value, because that's the most important value there that you need to consider when you compare functions. Now let's check here. See, they start with a point of intersection. That is where f of x is equals to g of x. That is where the two graphs intersect. So when you know when the two graphs intersect, then you can be able to locate a region where the other graph is above and the other one is below. But for you to be able to do that, you need a point of intersection. So now if you check here, we now check f of x greater or greater than g of x. Here they are trying to say if f of x is greater than g of x, what are they saying? Y value, the y value of the first function, the y value of the first function should be bigger than the y value of the second function. The y value of the first function should be bigger than the y value of the second function. What does that mean? It means that f should be above g. So you're going to check on your region of functions, where is the graph of f above the graph of g. But when they say f of x is less than g of x, they are looking for a region where the graph of f is below that of g. Now there's a special case here. There's a special case that you need to consider as well. They are saying f of x minus g of x is equals to 1. Once they start putting a number greater than 0, if it's a number after an equal sign, they put a number greater than 0, then you need to look at the following concept. You need to find a region where the first graph F is above the second graph G, and the distance between them is 1 unit. So here they explain that F is above G and the distance between F and G is 1 unit. That's very, very important. But you only look at that concept if the number after the equal sign is bigger than 1 or smaller than 1, but it cannot be equals to 1 when the number is not equals to 0. When that number is not equals to 0, then you are going to locate a region where F is above G and the distance between them is given by whatever number they put after the equal sign. However, now, if you look at this, if they were to put an equal sign, F of X minus G of X is equals to 0. If they put an equal sign, you can read it as F is above G and the distance between them is 0, or you can simply transpose then and say F of X equals to G of X. So it takes you back to the point of intersection. To the point of intersection. So you need to be careful. You are looking at core comparisons. You are comparing the functions there. Now we move on to combinations. Now with combinations, it's a different ball game now. It's a different ball game. Instead of looking at where the graph, one graph is above and one graph is below, we are now combining the two functions and checking where are they both above, or where is one above and the other below. So you are looking at those things. So what is important for that? The important skill is the signs that you learned in earlier grades, to say, if I multiply a positive sign and a positive sign, I'll always get a positive sign. If I multiply a positive sign with a negative sign, I'll always get a negative sign. If I multiply a negative sign together with a positive sign, I'll get a negative sign. If I multiply two negative signs, then I'll get a positive sign. Now, these skills there are important because we are going to refer to one portion of this as F and the other portion of this as G. Now, what happens is we are looking at now multiplication or division. So these signs here will hold. It is true also. What I've just written here is also true for division. It's not only true for multiplication, it's also true for division. So if we combine here the combination, what we are doing is we are multiplying functions, two functions, multiplying or dividing two functions. So that's where you see, oh, now it's a combination, because when I multiply, I want to get the combined effect. Even when I divide, I also want to get the combined effect. Remember, the inverse of multiplication is division. Just like in comparisons here, you talk about a minus sign here when you subtract. The opposite would be when you add. So you need to look out for some of those things there. So, but it's important that we are going to be looking at the concept of combination when we are multiplying two functions or we are dividing the two functions. But it's important to note, when you start to divide, just like in any algebraic what you call algebraic expressions that involve fractions, if you have a denominator and you have a variable in the denominator, it is true that if I have A divided by B, this would work only if this is defined, only if B is not equals to 0. Because if the denominator becomes 0, everything becomes undefined. So also with any algebraic function, so this will have a restriction that the function g of x should not be equals to 0 because it's a denominator. If it's equals to 0, if g of x is equals to 0, then the whole thing here will not going to work. It's not going to work at all if the denominator is equals to 0. So those are the things that we need to note. Now, if we look at where this starts, it starts when f of x times g of x is equals to 0. F of x times g of x is equals to 0. What does this mean to me when they say f of x is times g of x is equals to 0? This statement will only be true if g of x is equals to 0 or if f of x is equals to 0 or both. I'll repeat, for any product to be equals to 0, the first factor must be equals to 0 or the second factor must be equals to 0 or both the factors must be equals to 0. So in this case, in the context of functions, the first function must be equals to 0 or the second function must be equals to 0 or both the functions must be equals to 0. So we are looking at f of x equals to 0 or g of x equals to 0 or both. So where is f of x equals to 0? It's at what? At the x-axis. Where is y g of x equals to 0? At the x-axis. It is equals to 0 when the graph intersects the x-axis or the x. It is the x-intercept of the graph. So that's where we're going to start with our knowledge. Now, if you look at this now, we multiply. I'm just going to pick on a few. F times g. One graph is above the x-axis and the other is below the x-axis, because you can see the sign is negative. So we're going to check when the sign is negative. The sign might be negative if f is positive and g is negative, or it might hold if f is negative and g is positive. So those are the things that we should be considering when we are going to answer those questions. Obviously, as we go on, we will be doing some application questions. Now let's check this one also there. X times f of x is greater than 0. F times f of x is greater than 0. We are now looking at this now. We say it represents now the x-axis. So when both of these are multiplied and they give us greater than 0, which is a positive. Remember, greater than 0 means positive. So we're going to come back to our signs and locate where we can get what? A positive. That would be when both f and the x-axis are above or are positive, or when both are negative. So that's what we are looking at. Now, let's go straight to application. Right, but before that, let us also look at this important concept of increasing and decreasing function. Increasing and decreasing function. A function is said to be increasing if when the x values increase, the y values also increase. So if you look at any of the functions and you locate that maybe it is starting here, it's a straight line like this. If you check what happens to the value of x, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, like that. If you check now, what's happening to the y values, as x increases from minus 3 to 3, y values are increasing. From y is equals to 0 here, you can see that the y values keep on increasing. So if we have a situation where an increase in x values correspond to an increase in y values, then we say a function will be increasing in that interval. It's very, very important. So here we indicated that in mathematics, an increasing function and a decreasing function refer to how the function's value change as the input or the independent variable varies. Now, a function is considered to be increasing in an interval as the input values increase, corresponding to the output values. In the context of these functions, input we refer to that as our x values, and the output we refer to them as our y values. So as the x values increase, the y values also increase on a specific interval. If that happens, then we say the function is increasing. Now for a decreasing function, the opposite would be true. When x values increase from left to right, you get that the y values would be decreasing. So we refer to such a function at that specific or over that particular region. We will say that it decreases over the region there where you've located those values of x. You will see now that we are going to look at some application problems. Now, given the functions f of x is x squared minus 2x minus 3, g of x is x minus 3, you are given those coordinates there. A is negative 1, 0, B 3, 0, C 0, negative 3, and D 1, negative 4 are the coordinates of the x, the y-intercept, and the turning points respectively. Determine the values of x for which f of x is less than or equals to 0. So here they are saying f below x-axis. So where is the graph of f below the x-axis? We should locate that region. So this is the graph of f. This is the region on the graph of f that is below the x-axis. So this region can be shaded like that. So you can see that it's a region that starts at -1 and ends at 3. So we are going to say this is when x is trapped between -1 included and 3 included. So that's what basically it means to us when they say f of x. We need to locate that region where f of x is less than or equals to g of x. Now they're saying g of x is greater than 0. So they are asking where g is above x-axis, when g is above the x-axis. So we need to locate that region on a straight line. You can see this part of the straight line here is above the x-axis, and we need that region because we need the values of x. If you check, the values of x will start from 3 to infinity there. So we would say that all the values of x that are greater than 3, all the values of x that are greater than 3 would actually give you a region that is above the x-axis. Now they are asking when the graph of f is increasing. Now, if I were to just put in a rough sketch of that, if I were to put in just a rough sketch of that, only f, because they are talking about f, you know the turning point there is 1 and -4, like that. So they are asking us here, when is the graph of f increasing? I just explained to you that the graph increases in a region where when the x values increase, the y values also increase. Now if you check, if you read this graph from left to right, you can see that from here, what happens as x increases here, what is happening to y? X is increasing as you go this way. X increases from negative infinity to 0. X is increasing when you start here, moving that way. So you can see that as x increases, what happens to y? Y is becoming more and more less, or is decreasing. So until it gets to the turning point, and then when you look at the region after the turning point, you know the turning point is called a stationary point. It is a point where the graph does not increase nor decrease. So the graph does not increase, it does not decrease at the turning point, but when it moves from left to right, you can see the values of x are increasing, but the values of y are decreasing. But when you look at this arm now, this portion of the graph, you can see that as x values increase on the horizontal axis, the values of y are also increasing. That is why the graph is now going up there. So we say the graph will increase on this portion. How do we describe that portion? We describe it as x is greater than 1. That's how we describe that portion, because all the x values, for all the x values that are greater than the axis of symmetry, you get that the graph is now increasing. Right, we move on. Now determine the values of x for which f of x minus g of x is less than 0. Now here, if they put in the 0 for you there, always do this. Always try to do this. As long as the number there is 0, this is less than g of x. I transpose now the g of x because there's a 0 that side. So now you can see they want a region where f is below g. Now when they talk about a region where one graph is below the other, you need to first know the starting point. Where's the starting point here? It is where the two graphs intersect. So they intersect on this point and on that point. I will advise all of my learners to draw vertical lines on the points of intersection. Vertical line number 1, vertical line number 2. So where are these vertical lines? These vertical lines that I've just drawn occur or at x is equals to, what is x value here? X is 0. Also at x is equals to 3. That's where I've drawn my vertical lines. Now what I'm going to do is, obviously this is not included, so I'll do that. So these points of intersection, they represent what I call my critical values. So what I'm going to do now is I will check both the graphs on the left hand side of the vertical line and in between the two vertical lines and on the right hand side. So I will be looking at the graph from left to right, but now I'll be guided by those vertical lines. So how am I going to be interpreting this? I'm going to check on the left hand side of the vertical line, and then from there I'm going to look at the region in between the two vertical lines, and then I'm going to be looking at the region on the right hand side of the last vertical line. So let's check now. The first thing that we do, we check on the left. So from left to right, you can see that f here, this is f, this is g. So you can see that f is above. F is above, because if you look at the y value, if we look at the graph of a parabola, just on the left hand side, on the left hand side of the point of intersection, you can see that the parabola is above and the straight line is below. So we are not looking for that region. We are looking for the region where f is below. So this is not the solution. The left hand side, this is where we were checking. We were checking on the left. So let us now check in between the two vertical lines. When we check in between, we are now checking here. When we check in between, we want to check which graph is above, which one is below. You can see that this is f, this is g. Which one did you write above? It is g that is above, f is below. And here they want where f is below and g is above. So we have an answer there. I'm going to tick that one. We have an answer there. And then from there, we are done here in between the two. That is where we're moving in between the two. Now we are going to be checking on the extreme right hand side of the vertical line. Now we are going to be looking at this region. Now if you check here, this is f and then this is g. You can see now I wrote f above and g is below. So f is above and we are not looking for where f is above, which means our solution would be when x is in between, when the values of x are in between 0 and 3. So we're going to have that, therefore, For this, we're going to have that x is trapped between 0 and 3, like that. X is trapped between 0 and 3 because this is the region. This is the region we are interested in, where the straight line is above the parabola. Right, now let's look at this one now. G of x minus f of x equal to g of x minus f of x equals 2. So here we are looking for where g is above f and the distance between them is 2 units. Where g is above f and the distance between f and g is 2 units. Now, when you look at the point of intersection, if you start on the extreme left of the point of intersection, you can see that the distance between the graphs start to increase. You can see that at the point of intersection, they are equal, like that. But as you pass the point of intersection, the distance between them starts to increase. If we are to locate the maximum distance between them, then we need to check at the turning point. At the turning point here, x is equals to 1. Y is equals to -4. So here we have 1 and -4. Let us locate a vertical point. Let us locate a vertical point on the straight line. On the straight line when x is equals to 1. So if we can put 1 on the function g, g of 1 would be 1 minus 3, which is -2. So we know that this point here is when x is 1, y is -2, like that. Now, if we are to check those y values, what would be the y value? Let's check here. What would be the y value of g? Remember, I said g is above f and the distance between them is 2 units. How do we get the vertical distance? We would say y top minus y bottom. We have these points, 1, -2. We have 1, -4. So if you take y top, which is -2, minus y bottom, which is -4, you get that the answer is 2. So the vertical distance is 2 units. When does it become 2? When x is equals to 1. So it occurs when x is equals to 1, because it occurs along this line here, the line that I drew in red there. It occurs along that line. So along that line, y top minus y bottom gives me 2, which means yes, g is above f, and the distance between them, I worked it out as 2 units. And if it's given by 2 units, I'll check the values of x where I get the 2 units. So it occurs when x is equals to 1. I hope that you understand that one. Now, let's look at this part now where we are multiplying the two functions, where we now having our combinations. Remember, I said before, when we look at combinations, obviously we are going to be looking at the signs. The signs are important. When you look at combinations, the signs would be very, very important. Now, let us see those combinations now in application. Now, here they are saying f times g is greater than or equals to 0. Remember, this greater than or equals to 0 means positive. Greater than 0 means positive. So what are they looking for here? F above, g above. We are looking for two positive signs, or we are looking for f below, G below. So we are looking at two negative signs. That's what we are looking for. To get a positive, you need two positives or you need two negatives multiplied together. So now we need to put the signs on our graphs. But now remember, we were using vertical lines. Where do we now put in these vertical lines? We put the vertical lines on the x-intercept. So wherever you find the x-intercept, I'll put a vertical line. I have an x-intercept here. I'm going to put a vertical line there. I have another x-intercept here. I'm going to put a vertical line. Remember, this x-intercept also represents the point of intersection, but in this case we are taking it in the context of what? Of the fact that we are locating x-intercepts. Now I am going to do the same thing here and say my critical values would be -1 and 3. Those would be my critical values because that's where I drew my vertical lines. Now I am going to put signs on my graph. I will put a positive sign on the graph when it's above the x-axis, a negative sign when it's below the x-axis. Let's start with a straight line. Here it's above, so it's positive. Oh, it's a parabola. Positive, positive, and then this side negative, negative, because it's below all those negatives there. Here it's above the positives there. Then the straight line, you can see here it's below negatives all along here. Let me put them in a circle for the straight line. Negative and then positive, positive, positive. Now let us analyze. Remember, we are looking for F times G and it should be positive. So F times G and then the answer, whether it's positive or negative. Let's check on the extreme left because we are reading from left to right. Let's check on the extreme left of the first vertical line. You can see that this graph here is positive. This one is negative. You can see on the extreme left, we have a positive here. We have a negative there. So we have a positive for F and we have a negative for G. And when you multiply the two, positive times negative, you get a negative. And then you check now in between, the region in between the two vertical lines. If you check here, F, G is negative, F is negative. So what do you see? Negative and negative in between. It's a negative and a negative. When you multiply two negatives, you get a positive. And then you are going to check on the extreme right. On the extreme right now, going to check on the extreme right after this vertical line. We've checked here. We've checked in between. Now we should check here. Let's look now. If you look at the graph of G, it is positive. The graph of F is positive. Both of them are positive. So a positive multiplied by a positive, it gives you a positive like that. It gives you a positive. So your answer, remember, we said we are looking for an answer where we get what? A positive. So where do we get a positive? In between the two and after that. Remember, if this was included, our solution was just going to be any value of x that is greater than -1. But because this is not included, then we would have two sets of solutions. Our solutions for VI would be x should be trapped between -1 and 3, or x should be greater than 3. Alternatively, if you want to write it in another form, you can say all the values of x that are greater than -1 except 3. All the values of x that are greater than -1 except 3. So you are trying to say you go straight that way, but you exclude 3. Or you can write it this way to exclude it in your notation. So you'll choose which method works better for you. You can write it this way and then you skip this. you say x is trapped between -1 and 3 and x is greater than 1, or you can say all the values of x that are greater than -1 excluding 3. It's very, very important there. Now let us look at this particular question here. It says f of x divided by g of x should be greater or equals to 0. Remember here there is what? There is a restriction. What is our restriction? X cannot be equals to, or g of x cannot be equals to 0. So we do not accept any solution where g of x is equals to 0. Right. Now, let us check on this particular function. We are looking for a region here where f, they said positive. So we are looking for negative divided by negative, or we are looking for positive divided by positive. But we do have our critical values. Let us put them here. We have our critical values as -1 and 3. That's where the graphs were intersecting the x-axis. That is where we get our two vertical lines. Now, let us start again. We read from left to right. You can see from left to right, we've already done that. We've already done it here. Now, check what I'm going to do here. The difference between the two problems is that here, values are included because they said greater or equals to. So values are included. So in order to trace that now, we also have a restriction. G of x should not be equals to 0. Let's locate where g of x is equals to 0. Where is the straight line intersecting the x-axis? The straight line intersects the x-axis at 0 and 3. So this value would be included, but this will remain excluded. I will explain that again. It is excluded not because of the inequality there. The inequality was saying to us, include everything. That's what the inequality was instructing us to do. Include everything. However, there is that restriction. There is that restriction because there is division by g of x. So that natural restriction of a fraction would apply to say, but the graph of g should never be equals to 0. So you go where the graph of g is equals to 0 and say, no, let me exclude that particular point. Very, very important. We are excluding the point 3 because that's where the graph of g is equals to 0. Good. So now I am going to just put the signs as we did when you look at from left to right. On your extreme left, you can see on your extreme left that the parabola is above, the straight line is below. So when you multiply the two signs, you get a negative. When you look at the region in between the two vertical lines, you get to see that, okay, the straight line is below the x-axis, the parabola is below the x-axis. So if you multiply the negative and the negative, you get a positive. Also, when you locate on now the extreme right, from values that are 3 and above, you see also you get a positive. But here they were looking for a region that gives you positive. So the region that gives you positive here would be when x is greater or equals to -1, but x cannot be equals to 3, like that. Or you can write it, allow me to put it at the top here, or you can write it this way. You can write it this way. X is trapped between -1 included, 3 not included. Is trapped between -1 included and 3, or x is greater than 3, like that, or x is greater than 3, like that. Right, good people, we move on with our lesson. Now this one we are going to skip in the interest of time. We are going to skip this one so that we can also be able to cover the other concepts. Now we are looking at the concept of the roots. Very, very important concept. You've seen it asked in functions. They ask it a lot. Yes, in algebra, question 1, they will ask you about the roots, but there they will be wanting you to use your algebraic skills, the discriminant as well, for you to be able to talk to the nature of the roots there. But when it comes to functions, good people, they don't want you to do any algebraic manipulation using the discriminant. They want you to go to the graph, interpret the graph, and read the values of what they want from you directly from the graph. It's very, very important. Now, let's first check now what it means for us when we have a quadratic function. What does it mean when they say roots are non-real? They are saying to you the graph does not cut the x-axis, irrespective of whether it's a exponential graph, irrespective of whether it's an exponential graph, or it's a parabolic graph, or it's a trig graph. They are saying when roots are non-real, the graph should not intersect the x-axis. When they are saying roots are real and equal, so when they are talking about equal roots, they are trying to say to you that the function would be tangential to the x-axis, or the function would touch the x-axis once. You see here, it is touching only once, like that. So that is what it means when they say you have equal roots. When they say you have unequal roots, now you can see that this graph has the one root here and the one root there, and those roots are not equal. So that's when you have the unequal roots. So you can see also here one root there and one root there. Remember, by root we are talking about what? The x values. So you should never be confused and think that now when someone speaks of roots, it's talking about a big thing that you cannot manage. No, that person is simply saying to you the x values, but the correct mathematical term that we use, we refer to those x values as what? The roots of that particular function. Very, very important. Now, let us now start to investigate. Remember, investigative approach here, also very, very important. I am going to bring along some horizontal lines, and you are going to check for me how many times those horizontal lines touch or intersect the graph. And then from there, you are going to indicate the root, the nature of those roots. Now, if you check the first one, y equals to -9, is it touching the graph there? Of course not. It's not. So this has now non-real roots. The roots are non-real because that particular line does not intersect the function. Now, locate this one. Now, if you check this one now, intersects the function here and there. So it has what? And the roots are real unequal roots. What are the identities of those roots? X equal -2 or x equal 4. Those are the roots that this particular horizontal line is intersecting there. Now, let's also continue and look at another one. Now, looking at this one, you can see that it intersects here and there. You can see also the roots are unequal. And then you can see that now the roots are also real, but one root is negative and the other root is positive, like that. So that also comes to play when you start answering questions. Right. Now, let us look at the method that one can use in order to attempt most of these questions that have to do with nature of roots. Remember, the methods and the cases that I present with you here are not exhaustive of the whole concepts that you should know about roots. They just give you a way of being able to work with them. Questions can come in many different forms, but as long as you understand these fundamental concepts, then you'll be able to fight it out. You'll be able to respond to those questions. Now, explaining nature of roots using now the graphical approach. Explaining the nature of roots using the graphical approach. Now, case one, what happens is now they are going to give you at the function to say f of x equals to, and then when they start asking questions, in the place of f of x, they are going to put an unknown. So now that is saying to you, obviously I'm replacing f of x with an unknown, and I want to investigate what that unknown would be. So now the unknown is in the place of the y value of the function equation. For an example, consider if you look at y is equals to x squared minus 2x minus 3, and p is equals to x squared minus 2x minus 3. In the second equation, y is replaced by p. You can see here where there was y, you now have p there. So in order to attempt those questions, you need to move the line y equals to p vertically up and down. So you'll be moving the line just like we were doing here. If you still remember here, what I was doing was I was moving this line up and down. So you are going to be doing that in the function that is given, such that you are able to actually interpret what the question wants from you. So you move the line vertically up and down depending on the demands of the question. Please note that in this case, the graph does not shift, only the line y equals to p shifts. So you'll be moving that line y equals to p like that. Now with case 2, the unknown is in the place of the y-intercept of the function equation. For an example, consider now, if you look at these two equations, you can see that when there was negative 3, I have now replaced that, or I've replaced 3 with what? With k there. So I'm saying now the unknown is in the place of the y-intercept in the function equation. For an example, consider 0 is equals to x squared minus 2x minus 3, and 0 is equals to x squared minus 2x minus k. In the second equation, the value of the y-intercept negative 3 is replaced by k there. So how do you work with that? The method, you shift the graph vertically up or down depending on what the question demands, and trace what happens to the y-intercept as the graph shifts. So we're going to do some application on that. Now we present another case here, an extension to these roots. We present another case. Now the unknown is the horizontal translation. For an example, given f of x is equals to, you see, f of x is equals to x squared minus 2x minus 3, determine the value of m if f of x plus m. You can see now they've put in that x plus m there, which is our horizontal translation. So you can see x plus m is equals to 0, so x is equals to negative m, like that. So they are trying to tell you that the graph shifts to the left. The graph shifts to the left. So now, what does it mean in the context of these roots? You are going to move the graph horizontally to the left by m units depending on what the question requires. So for us to be able to do that, we need to also look at questions where we should be applying that particular knowledge. Right, good people, it's been an hour. We've been actually grasping a lot of knowledge, a lot of concepts in this hour. So I require that we just take a short break. Take a short break for 5 minutes, and then when we come back, we are going to continue. Just want you to stretch your legs and move around and get ready to apply the concepts that I've just taught you, to see how they are applied in problem solving. So your 5 minutes break starts now. Hello and welcome back. Let us go through some of the application problems on these nature of fruits. Right. Let's check now the first three questions here. If you look at this, you are told that the function f of x is negative x squared plus 2x plus 3 sketched alongside. Determine graphically, which means that they want you to use the graph, the values of k for which. Now if you check here, if you are to compare f of x is equals to negative x squared plus 2x plus 3, compare it with the question that is given, k is negative x squared plus 2x plus 3. You can see that the only change that they made here was that in the place of f of x, they put in what? K, which means that you are having a line f of x equals k. You are moving a line y equals k. So you want to move this line, this horizontal line, y equals k, such that you have equal roots. So what do you know about equal roots? We've looked at it before when we were still looking at those parabolas. For you to have equal roots, you need a horizontal line to touch the graph only once. So in order for you to have a line touching the graph only once, that line should be located at the turning point. So if you are to put this line here, if you are to put it there at the turning point, there, you can see that this line, if you put it at the turning point, you can see that it intersects the graph only once at that turning point. So that's what you are looking for, that because that's where you have equal roots. So this is the line y is equals to k, but already you know the y value at the turning point. At the turning point, y is equals to 4. But you know the line that you are moving is a line y is equals to k, which means that k is equals to 4, like that. So that's how you simply use the graph to get the answer. I'll repeat what I said. I said here, we've replaced what the examiner has done was, in the place of f of x, the examiner put k, and then now is demanding the values of k from you. So what you're going to do is you check, okay, my k is in the place of the y value, so which means that I'm moving a line y equals k such that I will have equal roots. So going to move that line such that you have equal roots. Now when you do that, then you get that the line should be k, or the line should be located at the turning point where y equals 4, which means k equals 4. Now let's check here, has non-real roots. If you check, the form is still the same. Instead of f of x, they put k. So we want to move a horizontal line y equals to k such that the graph will have non-real roots. Now if you check, if you put it above the turning point, and everywhere here above the turning point, everywhere, every place above the turning point, when you put that line, it does not intersect the graph, because that's what they want when they say non-real roots. They are saying, where is the line not intersecting the graph? So you see, when you put that line above the turning point, it does not intersect the graph. So it does not intersect the graph when the y value is greater than, is above the turning point, greater than 4, the turning point. But we know that the y value is equals to k, so we are going to say where k is greater than 4. So any y value above the turning point will not give me any solution. Now the third one, they are saying it has 2 positive roots. So they are specific to say these roots should be positive. If you check here, if you put the line here, this root is positive, this one is negative. So if they are looking for both of them being positive, you should locate the y-intercept. Check at the y-intercept. One root is equals to 0. One root is equals to 0, the other root is positive. Now check above. If we are to draw just the rough sketch here, just the rough sketch for what we are actually interested in. Now I want you to check above. If you are to put a line at the y-intercept 0 and 3, try now putting the lines above the y-intercept and below the turning point. Above the y-intercept and below the turning point, what do you see? The roots are both positive here. The roots are both positive. Why are we saying they are both positive? We have said here one root is 0 because x is equals to 0 there. But now x here is positive, x here is positive because we are on the positive x-axis. Also x here is positive, x there is positive. So that is where we are saying they are both positive, those roots, because the x value here is positive and the x value there is positive. So you can see that happens only when the line moves between the y-intercept and the turning point. Above the y-intercept, below the turning point, which means that now it is when the line y moves between the y-intercept, which is 3, and the turning point, which is 4, when y is trapped between 3 and 4. But we know we are moving a line y equals k, which means that k would be trapped between 3 and 4, like that. So that would be the solution to the third one. You need to look at this, try to make sense out of it. It's not difficult concepts here, even if it's not concepts you are used to, but these are simple mathematical concepts that need you to understand them conceptually, right? Let's look at now the other part here. Now if you check here, this now is different. Now the k here is put now in the place where there was the y-intercept. If you check, the y-intercept of this graph was 3. So that's where now they put the k. So now the question is changing altogether to say k is the y-intercept. So you want to know what the y-intercept would be when the graph has equal roots. What will the y-intercept be when the graph has equal roots? So now the trick is you have to move the graph so that it has what? Equal roots, and locate, as you move it, locate the y-intercept. I'll give you an example here. They are saying it has equal roots. So we move the graph so that it will have equal roots. When will the graph have equal roots? When it cuts the x-axis. So if I can move it up, it will never cut the x-axis. So the solution would be to move it down. If I move it down like this, you can see that now the graph cuts 1. So this graph, the new graph, the new graph has equal roots. But the question is about the y-intercept. What is the y-intercept when the graph has equal roots? It's not difficult to get it. What was the y-intercept when the graph was originally there? It was 3. The y-intercept was 3. Now everything moved down, including the y-intercept. So let's check how much we moved the graph down so that we can locate by how much the y-intercept would have moved. So we moved the graph from, now the coordinates here would be x does not change, 1 and 0. So you can see we moved the graph vertically down by 4 units. So if we move the graph by 4 units down, then the y-intercept also moves by 4 units down, which means this would be minus 4, which gives you k is equals to -1, like that, which gives you k is equals to -1. Now, because of the complexity of this one, where you have to first draw the graph that satisfies the condition, and after drawing the graph you need to locate the y-intercept of the new graph, because you have to shift the graph and then you have to locate the y-intercept of the new graph. I will not revert to this method. I will use another method which I believe is much easier, but you guys would choose your own way. This is the method that I will use, which I believe is much easier. I know with the previous problems I was just moving that horizontal line. Because I was moving the horizontal line, everything for me became a bit easier because the graph was not moving at all. So what I'm going to do now is I am going to go back to that method and check whether I can change this form to that original form. So I will then do this minus x squared plus 2x. I will then say, let me take my unknown k and make it the input and put it in the place of y. If I do that, then whatever that is left on the left hand side is now a problem because it is not the same as this. Oh no, it is not the same as the original function. So I cannot move a line on this particular function because that function has a +3. So in order for me to get the same function, I add 3 both sides. This now allows me to get f of x. Now this is f of x is equals to minus k plus 3. So what am I doing now? I'm moving a line y is equals to negative k plus 3, such that I will have equal roots. So where should I put this line for me to have equal roots? Where should the line y equal negative k plus 3 be for me to have equal roots? Obviously, for me to have equal roots, my line should be at the turning point. Now, what does that mean? If the line is at the turning point like that, it means that it means y is equals to 4. At the turning point, the y value is equals to 4. But my line of movement now is negative k plus 3, which means I have negative k plus 3 is equals to 4. Negative k is equals to 1. So k is equals to -1, like that. So this is the same as what we got there. It's the same as what we obtained there. K is -1, but using a different method. Now let's check the second one. Has non-real roots. This has non-real roots. So I know I have to put the line above the y value of the turning point to have equal roots. So I will have to say y should be greater than 4 for me to have equal roots. But now in this particular method, y is equals to negative k plus 3 is greater than 4. So if I continue with it here, I'll get that negative k is greater than 1. So k is less than -1, like that. So you are actually getting the values of k for which the graph will have non-real roots, like that. So which means that you can actually if you have non-real roots like that, you can actually say, okay, let's look at this again. For this graph to have non-real roots, y should be greater than 4. Y should be greater than 4, but y is negative k plus 3. If you transpose that that 3, you get k, negative k is 1, and you divide uniformly throughout by negative, the direction of the inequality sign changes. So k is less than negative 1. So that is correct there. Now let's move on. I have an activity here. I have an activity that I want you guys to do. It's a very short activity that you can do in 2 minutes. It does not require much from you. We just go through the question together. The function g of x is 2 over x plus 1. Plus 1 is sketched alongside the graph of g intersects the y-axis at t and the x-axis at the y-axis, at 0 and 3. The line y equals to x intersect the hyperbola in the first quadrant at S. Use the graph to determine the values of k for which g of x equals x plus k has two real roots that are opposite in sign. So I want you guys to try that in 2 minutes, and your 2 minutes start now. Good people, welcome back. I hope that you did this question to the best of your ability. It does not want a lot of concepts and a lot of time. It's not a long question. It just wants you to be able to interpret what they want from you. We've already read the question, so now we are check here. Use the graph to determine the values of k for which g of x equal x plus k will have two real roots that are opposite signs. So opposite signs means one positive, one negative. Now, if you check, this is a line y equal x. Now, what they did was, this is g of x. G of x is 2 over x plus 1 plus 1. This is equals to x plus k. If you are to look at this on its own, you will see it's the point of intersection between the hyperbola and that straight line y equal x. But now there's a k there that they've added, which means that they are saying you should move this line vertically up or down, like that, but you should slide it that way. Now, what we need to check here is that this k here is actually representing also the y-intercept of this line. So they are saying to you, in essence, what should the y-intercept of the straight line be for this straight line to touch the graph on two x values that are opposite in sign. I will rephrase that, or I will phrase it again. What is the y-intercept of the straight line for the straight line to intersect the hyperbola on two different x values that have also different or opposite signs? Now, if you are to put the straight line, this you move it, you start with it here. You can see that it is intersecting with 0 and with this point. But as you move it down like this, what do you see? It intersects the hyperbola on this arm on what? On the positive x-axis, but intersect the hyperbola on this arm on the negative x-axis. Anywhere where you put it now, it intersects on the negative x-axis and also intersect on the positive x-axis. Also, the original one, y equals x, intersect on the negative x-axis and also on the positive x-axis. So that's where you get the opposite signs. So you get those opposite signs when the y-intercept is below 3. That is there. So when k is less than 3, that is your answer there. So when you put that line such that it intersects at 3, as you move it vertically down, you can see that the line starts intersecting one arm. It starts intersecting one arm on the negative x-axis and the other arm on the positive x-axis, like that. So that's what was required of us. Right, now let us look at the extension of the roots, just like we did with the notes that I gave you, to say if it's now a horizontal transformation, they are saying now x minus p is the movement, so x is equals to p. So we know that graph moves to the right. The graph moves to the right. But now the question is, how many units should it move to the right to have two positive roots? If you check, this root is positive, but this root here is negative. So you want both the roots to be positive. So what should you do? You should move this root here that side. So how can you move? You can move to 0, and you can move to a value greater than 0 there. So it means the graph should be here. When the graph is here, when you've moved horizontally like that, then it will now have both the roots are now going to be positive. So if we can move the negative one arm, we move it to the right, it will then have two roots. So we want to move from -1 to a value in the positive x-axis. So, but the question is, by how many units should you move the graph so that you get that thing? It is by the number of units that are greater than what? Greater than 1. Because if you move it 1 unit, it will be on the origin. If you move it by exactly 1 unit, it will be located at the origin. But if you move it by more than 1 unit, then it would be on the right. That's what you want. Both the x values would be on the right hand side. I can actually test this just to show you that it works. When you say p is greater than 1, you can choose any value of p that is greater than 1. So you'd have f of -2. I'm choosing any value of p that is greater than 1. I'm choosing 2, which means that x minus 2 equals to 0. X equals 2. So if you move this graph 2 units to the right, you'll find it somewhere here. It will be intersecting there, which means this would be the root and the other one would be the root. So you can see that you get two positive roots. So what basically the examiner wants from you, he's saying to you, move the graph horizontally to the right such that it has two positive roots. And here you were disturbed by this root that was negative. So you're going to make sure that you move that root by enough number of units for it to start being positive. In this case, you had to move it by just more than 1 unit. Right. We move on. We finished our roots there. This was an activity, but because of time, we're not going to be able to do that. I want us to look at this hyperbola example as the last example of today. Last example of the day. I want us to actually look at this and try to solve some of the questions that this wants from us. The function f of x is x minus d over x minus p is sketched alongside where d and p are constants. The dotted lines are the asymptotes. B2, 0 is the point on f. The asymptote intersect at p. Determine the values of d and p, the values of d and p. Now we have a point here. We also have the asymptote there. So we know that this asymptote is x is equals to negative 1. It's x is equals to negative 1. And from this graph here, we know that x minus p equals 0, which means x is equals to p. What does that mean? We just worked out that x is negative 1, which means that p would be negative 1, like that. So we have the value of p. We now need the value of d. We can substitute on this form. Where we see f of x, that is y, we're going to put 0. Where we see x, we put 2 minus d over 2. Where we see p, we put negative 1. Like that. So we're going to get that when we multiply both sides by the denominator, 0 would be 2 minus d, which means that d equals 2. So we have p equal negative 1 and d equals 2. P equal negative 1 and d equals 2. So we've worked out the value of d and p. Right, we move on. Now show that the equation of f can be written as. Now if we check here, I started by substituting d that we calculated because we got d is negative 2 and we said p is negative 1. I started by substituting them here, so I get this equation there. That's the equation I'll be working from. So they say show that f can be written as y is negative 3 over x plus 1 plus 1. There are a variety of methods that you can use here, including long division and other methods that your teachers might have taught you. But now what I'll focus on here, I'll use this method, the method of being guided by the denominator. So what I do is, if the denominator is x plus 1, I am going to write down the denominator as x plus 1, but also write the x plus 1 in the numerator. So I am going to repeat the denominator in the numerator. So I would also have here x plus 1 in the numerator. But then I am going to ask myself, how can I get negative 2? Which number should I add or subtract to positive 1 to get negative 2? Because remember, at the end, this should always be x minus 2 over x plus 1. So I'm trying to write it as partial fractions. So for me to do that, I will need to then come back here and say, since I'm using the method where I'm guided by the denominator as my way of solving this, I will try to locate on the numerator the value of a constant that I should add to 1. What is it that I should add to 1? I have 1. What is it that I should add to 1 to get negative 2? So what you can add is, if you can subtract 3. So what happens? X plus 1 minus 3 takes you back there to x minus 2. So because of that, I will now do this, x plus 1 divided by x plus 1. I will say this is now my common denominator. If I have a common denominator, for an example, if I have a plus b divided by c, this can be written as a divided by c plus b divided by c. I can write it as partial fractions where c is the common denominator. So even here, I can write it as x plus 1 over x plus 1 minus 3 over x plus 1. So now you see that if you can allow me to continue with it here, that is my f of x, this would be 1 minus 3 over x plus 1. And the standard form would start with this part here, negative 3 over x plus 1, and then plus 1 there. So I was able to actually show that it can be written in the form of that. Now, we move on from that. Remember the method? I will write whatever the denominator is, I'll repeat it on the numerator, and then from there I'll look for a constant that I can add or subtract from the constant in the numerator that I just wrote, so that I can go back to the original given equation there. Right. Now determine the coordinates of P. Obviously, we have the equation now. We've written it down as f of x is equals to negative 3 over x plus 1 and then plus 1 like that. Let me just verify. Negative 3 over x plus 1, yes. So if you look at P here, P represents what? The point of intersection of the asymptotes. The point of intersection of the asymptotes, which means that I will then put both my asymptote here. So let's check the first asymptote. X plus 1 equals 0, x equal negative 1. The first asymptote, I get it from here. The second asymptote, I get it from there. And then y equals to positive 1. Therefore, my P will have coordinates negative 1 and 1, like that. Negative 1 and 1. Is f an increasing or a decreasing function? I think we have explained what an increasing or a decreasing function is, and now they want the values of x for which it increases or decreases. Now let us investigate the function from left to right to check whether it's an increasing or a decreasing function. We'll investigate it from left to right. Now, if we investigate the function from left to right and check what happens to the y values as the x values increase. So if you look at this from the left hand side here, where I'm highlighting, you can see that as x increases, y is also increasing for this arm. But it increases and stops there. And then from there, or it increases and becomes restricted by the asymptote. If we check the next arm from left to right, still when x increases, y is also increasing. So this arm is increasing. Also, this arm is increasing. What does that mean? It means the whole function is increasing. So D, we are saying it is an increasing function. It is an increasing function. Why is it an increasing function? Because when x increases, y also increases for both the arms of this rectangular hyperbola. Now, write down the values of x for which the function increases or decreases. Now, let's check for which values of x. When x starts from here up until the vertical line there. So when x is an element of, you can use this notation, minus infinity to negative 1, union starting from negative 1 to positive infinity. it increases for this arm. This left-hand side arm is defined from minus infinity to negative 1, and then the right-hand arm is defined from negative 1, the asymptote, to infinity. Negative 1 not included to infinity. Or obviously you can write it using our notation there to say x, it occurs when x is less than negative 1 or when x is greater than negative 1. So the first arm is located when x is located this side, the second arm is located that side. You are just indicating where the arms are located. That's where the graph would be increasing for both those particular arms. Right. Last question now. Write down the domain of G if G of x is equals to f of x minus 2. I'll show you two methods here of doing this transformation. The first method, what I'm going to do is I'm going to locate the domain and range of the original function. What was the domain? They said only the domain. So I'm going to locate the domain of f. What would be the domain of f? The domain of f, we can locate it because already remember we have the equation of the function negative 3 over x plus 1 plus 1. We can get the domain of f even from this sketched function. We can get the domain of f, that x an element of all real numbers, but x cannot be equals to the asymptote. The asymptote in this case is negative 1. That is the vertical asymptote. Is not defined on the vertical asymptote. It's defined everywhere, but not on the vertical asymptote. Now, we are going to check the transformation from f to g. Then we are going to transform the domain. What was the transformation from f to g? If you check, this is the transformation. X minus 2 equals 0. X equals 2, which means move 2 units to the right. If you move 2 units to the right, then the domain of G would be the same as the domain of F moved 2 units to the right, like that. It would be the same as the domain of F moved 2 units to the right, which means it's x an element of all real numbers, but x cannot be equals to 1, like that. That is the first method of being able to get what now? The domain after transformation has taken place. So what you need to do is understand the type of transformation and the number of units that the transformation has occurred, since this is the horizontal translation, and you'll say all the points in the graphs are going to move by those number of units, including the domain of the function. So now let's look at the second method, method B. Method B, what we do is we are going to get the equation of G. And then remember, G of x is f of x minus 2. So where we see x, on f, we are going to put x minus 2. So this is negative 3 divided by x minus 2 plus 1 and then plus 1. So the aim of doing this is that we find the equation of G and then conclude on the domain based on that equation. So now we're going to have that G of x is equals to negative 3 over x minus 1 plus 1. So that is the equation of what now? The equation of G. So to get the domain of G, what should we do now? We should take x an element of all real numbers. X an element of all real numbers, but x cannot be equals to what? The asymptote. So the asymptote in this case is 1. So x cannot be equals to 1. You can say, but x minus 1 cannot be equals to 0, which means x cannot be equals to what? Cannot be equals to positive 1. So if you check this domain here, it is the same as the domain that you got there, but using different methods. So you will always check with which method you are at most comfortable with, and actually try to be consistent in using that particular method. Right, good people, in the interest of time, I believe that we've covered everything that I wanted us to cover, but not all the problems that I had prepared for this lesson, but the concepts, we've covered all of them. So it is imperative that you go back to your schools, you go back to your books, to your textbooks, to your teachers. You go back there and apply and ask for questions where you're going to interpret these functions. Remember, as teachers, we can only do as much. We can only teach you those concepts to understand them, but it all comes back to you. At the end, it is the work that you do in our absence that is going to determine your success in our subject. So as a summary for this lesson, a learner should be able to solve inequality problems using graphical approach after watching this lesson. The learner should be able to determine or interpret nature of roots questions graphically after watching this video. The learner should be able to interpret variety of sketch functions and use the knowledge gained together with all the other functions and algebra, and then apply that knowledge in solving any questions that involve functions. So that's very, very important. Very, very important. Remember, good people, you need to practice. Mathematics is a subject that involves a lot of practice. Normally, they will say mathematics is done. You don't read maths, you practice mathematics. So please make sure you practice, and practice whilst it's still early in the year. Get used to the practice of mathematics. Get used to solving these complex problems. Then you'll do well at the end of the year. Thank you very much for tuning in. Please tune in again next week, where we'll be covering inverse functions. Take care of yourselves and take care of each other. Practice mathematics. Goodbye.